Okay, Assalamualaikum warahmatullahi wabarakatuh. And hi, see you again. So in this video, okay, we will do another example on property number 6 of Fourier transform, which is time differentiation. So in this example, okay, we need to use time differentiation property of Fourier transform to solve our Fourier transform for xt, which is signal xt is given by this pieces wise equation, which is 2t plus 8, okay, for t negative 4 and negative 3, and negative 2t minus 4 for negative 3, t is more than negative 3 and less than negative 2, and then 2t minus 4 is for t more than 2 and less than 3, and then last one negative 2t plus 8 for t more than 3 and then less than 4. Okay, else the value will be equal to 0. So if you draw this graph, so we will have this one, okay, for 2t plus 8, okay, which is this one. This is equation for 2t plus 8, but limited from t more than negative 4 and then less than negative 3. So this one is 2t plus 8, and then this will be negative 2t minus 4, and then this one is 2t minus 4, and then this one, this straight line will be equal to negative 2t plus 8. Alright, so we need to find what is our Laplace transform of xt, which in this question we are required to find what is our x omega. Okay, but we need to use time differentiation property of Fourier transform, which is given by this one. Okay, so dxt dt Fourier transform is equal to j omega x omega. So we need to differentiate our xt signal, our xt signal. Okay, so for this one we have we need to have another one, because this one is we differentiate one time. So for the case if we want to differentiate more than one time, so the property is extended to this one. So if we have dn over dtn and then xt, okay, and then Fourier transform of this one, okay, where we differentiate more than once. So the Fourier transform will be given by j omega and then power of n and then x omega. So the difference is that this one we differentiate one, and then this one we differentiate more than one, okay, which is depending on our n value, which is this is the same if n equal to 1. So we have j omega x omega, which is the same as this one. Okay, but this one we cannot use for n more than 1. So for more than 1 we can use these properties of time differentiation Fourier transform. So let's do this one. Okay, so we need to differentiate this one time. So when we do differentiate this, so we need to do part by part. Okay, so in this case we will differentiate this part, this part, this part, and this part. Okay, so we have dx dt. Okay, this will give us, when we differentiate 2t plus 8, okay, differentiation of 2t plus 8, so d 2t plus 8 over dt, this will give us differentiation of 8 will be equal to 0. Differentiation of 2t, this will give us equal to 2. Okay, right? So because of that, so we have from negative 4 to negative 3, so we will have value of 2 over here. So we have 2. Okay, so for the next one, okay, for negative 2t plus 4, same thing when we differentiate this. So we will have negative 2 because differentiation of negative 4 will be equal to 0. And then differentiation of negative 2t will be negative 2. So when we write this, so differentiation of negative 2t minus 4, this will be equal to negative 2. So we can draw this. It should be from 3, negative 3 to negative 2. Okay, this will give us value of negative 2. Right? And then we continue for the third part, which is 2t plus 4. So differentiation of d 2t minus 4 over dt, this will give us value of 2. So meaning that from 2 to 3, so we have value of 2. And then last one for 2t plus 8, so d 2t plus 8 over dt. Okay, this will give us, this one should be negative. Okay, negative 2t plus 8, so this will be negative 2. So we have here from this one from 2 and 3, and then this one from 3 to 4. Okay, so this one also negative 2. So we have this differentiation for xt, and then so we need to differentiate this one more time. Okay, because we don't have a delta function, so we need to differentiate this one more time. So for that reason, okay, so when differentiate this, okay, so we need to split this one in terms of this transition. Okay, and then we will look into this transition. So this one, okay, the first one, okay, I think I want to label this. So this is the first one, and then this will be the second, and then this one will be the third, sorry, and then until down here, and then we have fourth, and then we have the fifth one. Okay, and then same goes to here. We continue. This one 6, this one 7, and then this one until down here we have 8, and then this one is 9, and then goes this one 10. So we start from the left and then to the right. Okay, so if you look over here, when we differentiate for the second time, so we have dxt squared dt squared. Okay, so this will give us for part 1, okay, because we have transition, and then this transition is equal to, the amplitude is equal to 2, so that means we have delta function at t negative 4, so we have delta function with amplitude of positive 2. And then for a constant value of 2, okay, our dx dt or d to x we will differentiate this will be equal to 0, so we have 0 over here. And then for this part 3, okay, where we go down here and then until from 2 until negative 2, which is mean the distance is equal to 4. So for negative 3, okay, the distance is negative 4. Okay, right? And then the next one is that for this part, which is part number 4, okay, negative 2, when we differentiate negative 2, this will be equal to 0. And then the next one, it go up. Okay, when it go up from negative 2 to 0, so this, the distance is 2. So this will be a delta function with amplitude of 2. Okay, and then done for 1, 2, 3, 4, and 5. And then we continue for part 6 and the rest. So for part 6, we have transition. And then this one goes up. So meaning that we have a positive value. So this will be equal to 2 because of the distance is 2. And then differentiation of a constant will be equal to 0 for part 7. And then for part 8, it goes down, which is the distance is 4. Okay, so we will have a delta function at 3t equal to 3, which is with the amplitude of negative 4. And then for part 9, okay, it's a constant value, which is negative 2. That will be equal to 0 when we differentiate it. And then for part 10, okay, so we will have positive value, okay, which is equal to 2. Now we have a delta function, so we can write this. So d2xt dt squared is equal to 2, because we have the amplitude is 2, delta t plus 4, and then plus 2, not 2, I think this one should be minus for this one, minus 4 delta t minus 3, because we have at this one is at t equal to minus 3, and then plus 2 delta t plus 2. I think this one not minus, should be plus. Okay, and then the last, and then the next one will be t equal to 2. So you have 2 delta t minus 2, and then for this one, okay, so we have negative 4 delta t minus 3, and then last one is this one at t equal to 4. So we have plus 2 delta t minus 4. Right? So that this is our d2x dt xt dt squared. D squared xt divided by dt squared will be equal to this one. So we will differentiate, we will find Fourier transform for this one. So we will do Fourier transform for the left side, and then we'll do the same thing for the right side, okay, which is 2 delta t, okay, plus 4 minus 4 delta t plus 3, okay, plus 2 delta t plus 2. Okay, and then this will be continue. So delta t minus 2 minus 4 delta t minus 3, and then plus 2 delta t minus 4. Right? Okay, so we will this one, okay, based on our time differentiation properties, okay, which is this one. So for dn xt dtn, see the Fourier transform will be j omega n x omega. Since n equal to 2, so j omega power of 2. So f d2xt dt squared. So we have j omega and then power of 2 multiply with our x omega, because we use xt. Okay, so this will give us, when we do Fourier transform for delta function, of course this will be equal to 1 for delta function, which is this will be give us delta function, okay, which is based on Fourier transform pair delta function. The Fourier transform is equal to 1. Okay, so however we have shifting, we need to use shift properties because it's not delta t like this one, so it's being shifted. okay, which is this one advanced and this one is delayed. So we need to use time shifting property to find the Fourier transform, okay, which is this one. So we have e negative j omega t naught if you have x t minus t naught. Our case we have delta t plus 4 and so on. Okay, so we will use these properties so that we can get our Fourier transform. So remember this one t minus t naught, and then this will be t naught, and then if plus will be negative for the first one over here. So of course we have this one negative, this one positive, so t naught will be equal to negative 4. So this will give us 2, okay, e negative j omega t naught is equal to negative 4. Alright, and then we have x omega, which is referring to our delta t, which is equal to 1, okay, which is this one. Okay, delta t is equal to 1. So this will be multiplied with 1, okay, but I don't want to write this. And then we continue with this one, so negative 4. And then now we have plus 3, so we have negative e negative j omega negative 3. And then for that one you have 2, okay, use the time shifting properties, same thing, but now we have t naught is equal to negative 2. So you have e negative j omega negative 2. Okay, so we'll continue with the rest. So now we 2 and then t equal to 2. So we have 2e negative j omega 2, and then minus 4e negative j omega 3, and then plus with 2 for this one, which is 2e negative j omega 4. Okay, so that this is our d to x dt Fourier transform for d squared xt dt squared. And then we can simplify this equation. This will be equal to 2e j omega 4 minus 4e negative j, which is become positive omega 3, okay, for this one, and then plus 2e j omega 2, and then plus 2e negative j omega 2 minus 4e negative j omega 3 plus 2, okay, 2e negative j omega 4. Okay, so we can rearrange this equation. Okay, so we can rearrange that. So we will look in terms of the exponential, complex exponential term, which is, for example, ej omega 4. The conjugate is this one, so we will put it this one together. So we will have this 2ej omega 4, right? J omega 4. Okay, so plus 2e negative j omega 4, which is this one, and then next one will be 4e j omega 3, and then negative 4e negative j omega 3, and then last one is for 2e j omega 2, and then plus with 2e negative j omega 2, which is this one. Alright, so we continue the calculation. Right, so we will continue our calculation. So I just write down again the equation. So we have j omega, we have j omega squared x omega, this will be equal to 2e j omega 4 plus 2e negative j omega 4, and then minus 4e j omega 3 minus 4e negative j omega 3, and then last one will be plus 2e j omega 2 plus 2e negative j omega 2. Alright, so the next one is that we can we can use a Euler relation so that we can represent this complex exponential into cosine term. So we have 3 cosine term that we can produce. So let's do it. So this will be equal to, we can factorize this one. So we have 2 and then e j omega 4 and then plus e negative j omega 4, and then negative 4 we factorize it, so we have e j omega 3 plus e j negative j omega 3, and then the next one will be plus 2 e j omega 2 plus e negative j omega 2. So in order to use Euler relation, we need to have half e j omega 4 negative j omega 4 so that we can transform this one into cos omega 4. So what we need to do is that we need to multiply with 2 over 2. Okay, so this will give us 2 over 2, and then multiply with e j omega 4, okay, plus e negative j omega 4, okay, and then this one, and then negative 4 2 over 2, which is e j omega 3 plus e negative j omega 3, and then last one will be plus 2, okay, 2 over 2 e j omega 2, okay, plus e negative j omega 2. Okay, so this will be equal to 2 will be go outside, so you have 4 half e j omega 4 plus e negative j omega 4. Alright, and then this one will be equal to negative, sini over here, negative 4, okay, and then will be multiplied with 2, so that means this one will be negative 8, 1 over 2 e j omega 3 plus e j negative j omega 3, and then last one will be you multiply 2 with 2, so you have 4 half e j omega 2 plus e negative j omega 2. So we can use Euler relation for this case. So this will give us, okay, 4 cos 4 omega, and then negative 8 cos 3 omega, and then plus 4 cos 2 omega. Okay, so we have this one, okay, the Fourier transform for this one. So you have j omega squared x omega. So now we can find our x omega. Okay, we just need to bring j omega squared to the right of the equation, which is we need to divide the right equation with j omega squared. So x omega, okay, which is what we want. So this will be equal to 4 cos 4 omega minus 8 cos 3 omega plus 4 cos 2 omega. So this will be equal to, and then we need to divide this with j omega squared. Right? So j omega squared. So j omega will be equal to -1. So we can have here j omega squared will be equal to -1. So we have 4 cos 4 omega minus 8 cos 3 omega plus 4 cos 2 omega divided by j squared will be equal to -1 and then omega squared. So -1, and then we can also factorize this. So we will have -4 and then factorize it. So cos 4 omega minus 2 cos 3 omega and then plus cos 2 omega, and then we divide this into omega squared. Right? So this is our Fourier transform for our signal xt, which is x omega equal to -4 cos 4 omega minus 2 cos 3 omega plus cos 2 omega divided by omega squared. Right? So hopefully you understand how to use time differentiation properties, okay, to find our any signal Fourier transform. But you need to remember that, okay, so you need to remember when we do multiple differentiation, so we need to use this one, okay, which is d and d power of n, and then dt and xt, okay, and then this will be equal to j omega n and then x omega. So this one is for which is first integration, and then this is for more than one the differentiation, sorry, this one is for just differentiation for one time, and then when you want to differentiate more than one time, so we will use these properties. Right? So hopefully you understand how to use time differentiation properties to find Fourier transform from for any signal which is in time domain, and then we will transform it into frequency domain. Okay, thank you for watching, and then see you again. Okay, bye.